This video is going to give you an introduction to hypothesis testing. Here's the general idea behind hypothesis testing. We have some population with an unknown population parameter, either the mean mu, the variance sigma squared, or the proportion p. For today, let's focus on an unknown population mean mu. Our ultimate goal is to learn as much as we possibly can about this unknown parameter by performing inference on the population. What we'll do is we'll make a guess about what we think the value of the parameter is. We'll take a random sample from the population. We'll compare the sample mean x bar to our guess for what the true population mean actually is. And then in the end, we'll decide whether or not we think our guess was a good or a bad estimate of the population mean. Consider this example. You're in a class of 500 students and you've just gotten an exam back. The ultimate goal here is to determine what the mean exam score was for the entire class, the population mean for the entire class. Now, your professor doesn't tell you the population mean, and it's not practical to go around to all 500 students and figure out their individual exam scores. You guess that the population mean is 80. But thinking back, the test was pretty difficult, so if you're wrong, you think that your guess is a little bit too high. Now, with this information, what are we able to do? What we're able to do is the first step in a hypothesis test. We're able to set up the null hypothesis and the alternative hypothesis. The null hypothesis is the assumption that you make about a population parameter. In other words, the null hypothesis represents your initial guess about the value of the parameter. The null hypothesis is always denoted by H0. In this particular case, since we're working with the population mean, we're going to write the null hypothesis as H0 followed by a colon. Then we'll have the Greek letter mu for our population mean, and we set that equal to mu0, where mu0 is our hypothesized mean. Mu0 is our initial guess about what we think the true population mean actually is. Now, the alternative hypothesis is the conclusion that you come to if your null hypothesis is incorrect. The alternative hypothesis takes on one of three forms, and the form of the alternative depends on the wording of the problem. The alternative hypothesis is always going to be denoted by H1, and we write out the alternative hypothesis based on if we have what's called a lower one-sided test, an upper one-sided test, or a two-sided test. In a lower one-sided test, the alternative hypothesis is going to be H1, which is mu less than mu0, mu less than our hypothesized mean. In an upper one-sided test, the alternative hypothesis is mu greater than mu0. And in a two-sided test, the alternative hypothesis is going to be mu not equal to mu0. We don't necessarily know which direction we're looking, if we're looking greater than or less than our hypothesized mean. In a two-sided test, we basically just say that our population mean mu is not equal to our initial guess. Now, for this particular problem, we initially guessed that the mean exam score was equal to 80. But since the test was pretty difficult, we thought that if we're wrong, our guess was a little bit too high. What this means is that the null hypothesis is going to be H0, mu equal to 80, and the alternative hypothesis is going to be H1, mu less than 80. We think that our exam score is 80, that's represented in the null hypothesis, but if we're wrong, we think that 80 is a little bit too high. We think that guess is too high. So in the alternative, we reflect that notion and we say, if the null hypothesis is wrong, we think the alternative is true. The alternative is going to be mu less than 80. I want to give you some important facts about the null and alternative hypotheses. In hypothesis testing, we always assume that the null hypothesis is true until we can prove it false. We always assume that our initial guess is going to be correct until we can gather enough evidence or enough information that tells us that it's definitely wrong. Your hypotheses are always going to refer to a parameter like mu, sigma squared, or the population proportion p. You will never have a statistic like x bar or s squared or p hat inside your hypotheses. And you're going to want to use the context of the problem to determine the form of the alternative hypothesis. It's not always cut and dry, it's not always obvious, but if you read into the problem, you can figure out what the alternative hypothesis should be. Now, to continue along with this scenario, what we're going to do to figure out what the mean of the population is we'll take a random sample of your classmates to estimate the population mean. We'll take a random sample of 12 students, and once you're done with this, and these 12 students tell you what their exam score was, you find that the sample mean of these 12 observations was 74. Now, your professor won't tell you the population mean, but he will tell you that the population standard deviation for the class is equal to 10. Now what we have is a sample size, 12, a sample mean, 74, and a population standard deviation of 10. Again, we have to assess what we can do with this information. The first thing we can do is we can measure how many standard deviations 74 is away from 80. How far away is our sample mean of 74 from our guess of 80? Once we have that, we can determine how likely it is that we would get a sample mean of 74 if the true population mean is actually 80. If we're sampling from a population where the mean of that population is actually equal to 80, our initial guess, we want to know how likely it is that we would get a sample mean of 74. Because 74 isn't necessarily that close to 80, we want to figure out if that's likely or not. The way we do this is by calculating the test statistic. The test statistic is the criterion that we use to make a decision about if our guess for the true population mean is actually true. In other words, it's a measure of how far away our sample statistic is away from our hypothesized population parameter. How far away is x bar from our hypothesized mean mu naught? Now, the test statistic is going to change depending on the situation that we're working with. We have to figure out how many populations we're comparing, and we have to look at what parameter that we're interested in. In this particular case, we have one population, and we're interested in the mean of that population. Our population is the 500 students who are in this class, and we're interested in the mean exam score for these 500 students. So in this case, our test statistic is going to be the number of standard deviations that the sample mean is from the hypothesized mean. How many standard deviations is 74 from 80? Now, we know that we have a random sample of 12 students, and the sample mean exam score for these 12 students is equal to 74. We also know that we have a population standard deviation of 10. Our ultimate goal here is to figure out how many standard deviations 74 is away from 80. The way we're going to do this is by taking 74 and standardizing it using our hypothesized population mean of 80. Our test statistic is going to be 74 minus 80 divided by 10 over the square root of 12. Notice that this is the exact same equation that we used to standardize the sample mean a couple of classes ago. It follows a standard normal distribution, which is why we have the z out in front. And this equation here literally tells us how many standard deviations 74 is away from 80. Working this out, what we end up with is negative 2.08. So in the end, this tells us that our sample mean of 74 is 2.08 standard deviations below 80. The next thing that we need to do is assess what this means in the context of the problem. What does it mean to have a sample mean that's negative 2.08 standard deviations from our hypothesized mean? What we're going to do is calculate something called the p-value. The p-value is the probability of obtaining a test statistic that is equal to or more extreme than what was actually observed from the sample if the null hypothesis is true. So think about it this way. We hypothesized that there was a population mean of 80. We got a sample mean of 74, which corresponded to a test statistic of negative 2.08. Our sample mean was 2.08 standard deviations below the hypothesized mean. The p-value is the probability that we would get a sample mean of 74 or less if the true population mean is actually equal to 80. You can think of the p-value as a measure of how unusual the test statistic is, assuming that the null hypothesis is actually true. The way that we calculate the p-value depends on the form of the alternative hypothesis. It's denoted by the lowercase letter p, and ultimately, small p-values tell us that our guess for the mean is probably wrong. A small p-value tells us that our sample mean was unusually far from the hypothesized mean. So either we got a bad sample, or our guess for the true population mean is wrong. So small p-values are an indication that our guess for the mean is probably wrong. On the other hand, a large p-value tells us that our guess for the mean is likely to be relatively close to the true population mean. We already know that our sample mean is 2.08 standard deviations below the hypothesized mean. We know that 74 is 2.08 standard deviations below our guess of 80. What we need to figure out now is how unusual this result is if 80 is the true mean exam score. How strange is it for us to get a sample mean of 74 if the true average exam score in the class is actually equal to 80? What we're going to do is take our test statistic, negative 2.08, and plot it on the standard normal distribution curve. Now keep in mind, our null hypothesis was mu equal to 80, and our alternative hypothesis is mu less than 80. The p-value is the probability that we would get a test statistic as extreme or more extreme than the one that we originally got. In this case, since we have a lower one-sided test in the alternative hypothesis, the p-value is going to be the area to the left of negative 2.08. So, since we're working with the standard normal distribution, the p-value is the probability that z is less than negative 2.08. Looking this up inside the standard normal table, we find that this probability is 0.0188. I want to do a quick recap to remind you how we've gotten to this point. You're in a class of 500 students and you've just gotten an exam back. You think that the average score in the class was an 80, but if you're wrong, you think that your guess might be a little bit high. You take a random sample of 12 students, and you find that the sample mean score of these 12 students was a 74. 74 was 2.08 standard deviations below your guess of 80. And so the probability that you would get a sample mean of 74 or less if the true population mean score in the class was actually equal to 80, that probability is 0.0188. So taking everything that we have here, what can we do with this information? what we're going to do is assess how good our guess of 80 actually is. Either 80 is a good guess for the population mean score, or 80 is just too high. We can make two possible decisions about the hypotheses in a hypothesis test. The first decision that we can make is to fail to reject the null hypothesis. We'll fail to reject the null hypothesis if the p-value of our test is too large. What this means is that your guess for the population mean is relatively close to being correct. The sample mean might not have been exactly equal to the hypothesized mean, but it's in the neighborhood. The other decision that we can make is to reject the null hypothesis. We'll reject the null hypothesis if the p-value is sufficiently small, and as a result, we'll conclude that the alternative hypothesis, H1, is true. What this means is that your guess for the population mean is wrong. You were just too far away from the sample mean for it to make sense that your hypothesized mean is actually the true mean of the population. A hypothesis test is considered to be statistically significant if the null hypothesis is rejected. Now, just as a side note, we'll discuss what too large and sufficiently small mean in class. For this particular problem, here's our decision-making process. 74 is 2.08 standard deviations below our guess of 80 for the population mean. If 80 is actually the true population mean score for the exam, the probability that we would have gotten a sample mean of 74 or less from a population where the mean is actually 80 is 0.0188. So the probability that we would get a sample mean that small if the true mean of the population was actually equal to 80 is less than 2%. This is a relatively small probability, and so what this tells us is that it's unlikely that the true population mean is actually equal to 80. Since we have a small p-value, a small probability, our decision is going to be reject the null hypothesis. And so the conclusion that we're able to come to is that the mean test score is actually less than 80. I want to give you just a couple other notes that will set you up for the next several weeks. Throughout the rest of the semester, we're going to encounter many different types of hypothesis tests. What I've just shown you is one type. Each test that we do from here on out is going to follow the exact same 5-step procedure, which I'll detail in class for you. It'll make doing a hypothesis test relatively straightforward. Each test is used under different conditions and has a different test statistic. Again, we'll talk about the different conditions and the different test statistic as we come across them in each future lecture. Most importantly, we'll use the context of the problem to determine which test we need to use. In this particular case, looking at a single population, where we're interested in the population mean, we performed what's called a z-test. The z-test is a specific type of hypothesis test that's used for performing inference on an unknown population mean. In order to perform the z-test, you have to know the value of the population standard deviation. You have to know what sigma is. If you know the value of sigma, you can calculate the test statistic and perform inference on an unknown population mean. In this case, our test statistic is going to be x bar, the sample mean, minus mu naught, the hypothesized mean, divided by sigma over the square root of n, the population standard deviation divided by the square root of the sample size. This test statistic follows a standard normal distribution, and it's literally a measure of how many standard deviations the sample mean is from the hypothesized mean. So this video gave you a general idea of what we do in hypothesis testing. We have a population, we have an unknown population parameter, and we want to learn more about the value of that population parameter. So what we do, we make a guess about its value, take a sample from the population, and we compare the two. We look to see how close that sample statistic is from our hypothesized value of the population parameter. What we did here was a z-test. We were performing inference on an unknown population mean. There are a number of other tests that we're going to cover throughout the next couple of weeks, but for right now, focus on this scenario. An unknown population mean where we know the value of the population standard deviation. That is what your z-test is.